We're honored to have back with us one of our very own alumni now making waves in the industry. G Aswin, currently a computer GPU performance engineer at Intel. Ashwin's journey has been nothing short of inspiring. In 2022, he secured an All India rank of 841 in GATE Computer Science exam, competing against nearly 1 lakh candidates, a testament to his dedication and technical acumen. He's also been an active contributor in communities like Google Developer Student Clubs and Big O at RNSIT, always eager to learn, share, and lead. Today, Ashwin will walk us through the cutting edge techniques and hardware strategies that enable fast training and inference of AI models. Whether you're a beginner curious to know about chips and code interact, or an advanced practitioner looking to optimize your own workloads, there's something in this talk for you. So, without further ado, please join me in giving a warm welcome to Ashwin. Let's make the most of this opportunity to learn from his experience and dive into the real world of AI acceleration together. Welcome, Ashwin. Thank you for being here.
Yeah. Thanks for the warm welcome and the introduction. Yeah, as you mentioned, I am an alumni and graduated from here 2023, and I've been with Intel since then, and I've been an intern at Intel throughout my fourth year. So it's been almost 2.5 years, and working with this particular team, I've got a lot of chance to explore a lot of new things for me personally, because there's a lot of things that of course we learn in college, but that's just scratching the surface in terms of what's actually happening in the industry. And that's one of the motives for this presentation. It's not to go particularly in depth of any particular topic, because that you can always do, but this presentation is to connect the dots of what you learn in college and um, try to see how that actually is in practice when you go into the industry. I've had a session earlier, I think almost a year back, when I was talking about compilers. I tried to make sense out of that subject. Why do you learn that in the first place? And there are a few subjects in our computer science syllabus that people don't really think is that important, because if you're only into web development, you'll think data structures, algorithms, and pretty much that, and databases. You would think that's the only thing that you use. But there are careers out there which make use of compilers, computer architecture, operating systems, and that's what I'm here for, to talk about those. Right. So, since this is a very high level uh, presentation, feel free to stop me at any point if you have any doubts or queries, and we'll take that. As per the slides are concerned, I don't have a lot, so it's supposed to be an interactive session. You can ask questions anytime. Right. So, with that being said, this is the agenda that we're looking at. Uh, I will go into some level of details on AI workloads, because that's one thing that's really trendy these days. And that's something that we use almost every day at this point. And that generates a lot of interest. So I'm here to tell you that with AI being a new topic in the industry, at least in the usage perspective, it's nothing new in terms of what it actually does, right? And it might seem like something that's very cutting edge, but people have been working on these things for a long time, and that's where you can try to relate that today. It's just the top level algorithms that have changed and the front end that has changed, but these things have existed for a long time. So we'll try to see what exactly is a AI workload uh, at the compiler level, and then we'll see why do you need GPUs in the first place. Because I think as far as users, we and our personal machines, we are mostly concerned with CPUs, and what we learn in computer architecture in college as well is all about CPUs. But GPUs become a very important piece of hardware when you talk about AI. So we'll get into that. We'll see why GPUs are important in the first place, and we'll talk about that because my team personally works on the GPU products. So That's where I can give you more details, and we'll try to see how you think in the hardware level, in the sense that as a programmer, as a computer science student, what do you need to know about the hardware? Because it's not like you'll be designing hardware at any point in your career, but you will always be running it in one of the hardware machines. So you need to know what the hardware machine looks like, at least on a theoretical level, to write the best possible code for it. And we'll also see an example of how that matters. Uh, we'll talk about performance because that's also one thing that I do. We'll try to see how do you maximize your performance and at various levels, at the code level, at compiler level, at hardware level. You can do all that. And then we'll wrap it up and then we'll take questions. So yeah, so we'll be talking about AI workloads, right? So when I say workload, what does it mean? So workload is anything that you're running on your hardware. So if you're just writing a C program and compiling it and running it in your CPU, that program is your workload. So when we talk about workloads, we think in a perspective from the hardware's perspective, right? So as a hardware engineer, one person will think what is being ran on my hardware so that I can make the most of it and try to make it as optimized as possible, right? So in our perspective, AI workload is nothing but the code that actually ends up running. So these days, GPT is all the hype, right? So GPT is, in the end, if you break it down, it's nothing but a bunch of matrix multiplications. I don't know what's the semester level at which people are here, but you'll end up having a subject where you see what a neural network looks like. But in the end, it's nothing but a bunch of multiply and addition operations, right? So you keep multiplying over and over again, and then you get the weights, and then that helps you predict things. That's how a neural network works, and that's the basic logic in a LLM, large language model, as well. So uh, in GPT, the T stands for transform, right? So the transform operation is again something that uses a lot of multiplications. So we see a pattern, right? We see us talking about multiplications a lot. Now, yeah, so that's what your AI workload looks like. And that point is important because we'll come to that soon of why we keep stressing on the multiplication part. So just breaking down the AI workload, you'll see that there are training workloads and then there is inference workload. Now, this is also something that you might see in your course soon, but training is basically setting up the model to eventually answer things, right? So when you train the model, you set up the parameters, you set up the all the points that you will be using in the end to predict stuff. So that's the training part of things. So basically, you're creating a model, you're teaching it something. That's the training part, right? And inference is actually using the model that you created in the training part and then trying to make some data out of it, right? You'll give an input, you'll get an output, and that's the inference part of the workload. So why do we break it down? We break it down into these two steps because both of them have very different requirements. The training part is very compute intensive in the sense that you'll be doing a lot of math to generate your parameters. So I think these days the GPT and large language models have like millions of parameters. So that's very compute intensive. It's not something that you could usually run in your laptop or something like that, right? You usually get a GPU to do that. We'll see why. And the inference part, on the other hand, it's not very compute intensive, but it's very memory intensive. So when I say memory, you have to bring in a lot of data and then load a lot of data out of the GPU. So when we see both of these, right, we see that the requirement might be slightly different for both. So that's why we segregate these two. But that's what a AI workload looks like, right? Uh, Now, you might ask, why would you need a different hardware in the first place? You have laptops, you know that these laptops and these phones are very capable in terms of compute. You, whenever you want to buy a phone or laptop, you always see the specs, right? You see what is the memory, what is the CPU capable of, and all those parameters you see. But if they are that powerful, why don't you just use them to train your AI models and then inference, right? Why do all these companies invest so much money in building their GPU infrastructure? And that's where you see the concept of parallelism comes, right? So if I'll get to that point, it will be a lot more clear when you look at the diagram of what a GPU looks like. But basically, it's how a screen works, right? A screen might have thousands of pixels, right? A CPU, what it will do, it's very good at calculating one particular pixel at a time, right? Or maybe four at max or eight at max parallelly. So what you end up doing is you keep calculating each pixel's color one at a time. And that's not very efficient because you need to render the screen 60 times a second. And then there are thousands of pixels, millions of pixels in a screen. So that doesn't sound very efficient, right? You would want a lot of parallel things, a lot of parallel compute engines doing the same thing. So it's not a very complex task you're doing. It's just a pixel grid. So you would want a lot of parallel people working on the same thing and then giving the output at a time, right? So that's where the concept of parallelism comes. And then when I talk about matrix multiplication, right? So when I said AI was able to do a lot of multiplications, it's not small 2 by 2 or 4 by 4 multiplications. These are at the scale of thousands of rows and columns, usually 4096 into 4096 or something at that scale, right? And when you're doing at that scale, if you have done matrix multiplication, you know that there's a lot of operations that you have to do. Now, again, concept of parallelism comes. It doesn't make sense to do these things one row, one column at a time. So when you write a C code to do matrix multiplication, right, there are 3 for loops, and basically the time complexity is at the cube level, right? It's not very efficient to do it one at a time, especially at that scale. You can try to write a code for matrix multiplication and give an input at the level of hundreds and thousands of rows, your PC will probably crash because it doesn't, or it will take forever to do that computation. So that's where you'll see that GPUs do it in seconds, right? Um, you see specialized hardware. I'll show you that when we go to the diagram. Memory bandwidth and HBMs. HBM is nothing but high bandwidth memory. Again, at CPU level, you might have few gigabytes per second that you can transfer out of the CPU and into the CPU. When we talk about AI GPUs, it's at the scale of terabytes per second. And that's really helpful when you're doing inference because you have to pull a lot of data in and pull a lot of data out of the GPU. That's where high bandwidth memory comes. And of course, the software ecosystem has to be present because you cannot do anything with the hardware if you don't have an interface to interact with it. So all the things in terms of APIs, drivers, compilers come in between the hardware and software. So there's a lot of scope for you to maximize performance at each level. It's not like hardware can do it on its own or your code will do it on its own. You need to interface it properly so that you're utilizing your hardware the best way possible, right? So when I said parallelism, this is what I meant. This is a very simple diagram. In the next slide, I'll show you what a real GPU, at least at a scale, looks like. But this is what a CPU will look like at the top level. It's not bad, right? You have 4 cores here. It's good. Each compute core is capable of doing pretty complex operations. If you remember from computer architecture, there is CISC and RISC, right? So CPUs usually fall in the CISC category, at least the x86 Intel and AMD CPUs, where there are a lot of operations that you can do, very complex ones at that. So CISC basically stands for complex instruction set architecture, right? When I say instruction set, it's the operations like addition, multiply. These are the simple ones, but the CPU instruction set is so huge that it can do very complex operations in a single instruction. So when you compile your code, when it becomes assembly, the assembly code is really neat in terms of CPU. You don't have a lot of instructions, but each instruction is quite complex. And that's where a CPU shines. A CPU shines at doing instructions very quickly, but not in a very parallel fashion. So in this case, you have 4 cores. If you have multi-threading at max, each core can do 2 threads at a time. So only 8 threads here running parallelly. It's not that good when you're talking in terms of AI operations like matrix multiplication or something like rendering a screen. On the other hand, if you see GPU, each blue box that you see here acts as a core. EU stands for execution unit. And each of these is capable of doing 8 threads at a time. So you can imagine, right? In this case, this is a very simple GPU, I'll say. It's something that looks out of a laptop or mobile. But if you go to an AI GPU, if you look at an AI GPU architecture, it stands at thousands of cores. So you can imagine the parallelism, right? Each core, even if it's doing one multiplication at a clock, you suddenly have improved your efficiency by a factor of 1,000, right? So that's where a GPU shines. And of course, you cannot just have execution units or what do we call it in computer architecture? It's a it's the thing that does math, basically ALU, right? So it's the ALU, and ALU alone, it's not going to do everything. We'll see that in the next slide. The yellow box that you see here is a local cache. We'll call it L1 cache. And anything that's hit in L1, that's great. You can get it for each of these execution unit. And anything that's a miss in L1 will go to L2. You can fetch it in L2. And if it's not there in L2 as well, you can go to main memory, right? So that's what a GPU architecture looks like from top. Now you might think, why am I talking about hardware uh, computer science people, right? It's not like you're going to design these things, but you're going to write code which is going to run in both CPU and GPU. I think till now we are only exposed to writing code for CPU, so our mindset is stuck at that. Our mindset is writing for loops and assuming that the thing is not going to run parallelly, but that's not true. That's not the case when you're actually writing things in production. You always use parallelism. Even if you're not from this background, even if you're a Java developer, there's always some multi-processing, multi-threading that you'll have to do to enhance your performance. So think in that perspective, right? And the diagram that I showed earlier was um, a simple representation of what a GPU looks like. This is something that is a bit more accurate in terms of what the actual product will look like. Now, this is a proper, I think, a laptop GPU. So you will also see some 3D units, right? You'll see geometry, you'll see rasterizer, you'll see pixel color, backend, front end, you'll see tessellation and all these things. Now, these things, again, these are things that you'll hear in your computer graphics subject. Those are the terms that you'll hear. And these units help you render things in the screen, or when you're gaming, when you generate the frames, these are the units that help us generate the pipeline. And then eventually the actual multiplication, math, addition, all of that is done in the execution units only, of course. But the pipeline is different. Now, GPUs from the early days only were designed to do uh, pixel render, right? But people realize that when you have a lot of compute power, you can probably use it for scientific applications. You'll use it for these math operations very quickly. So that's where people started repurposing their GPUs to skip the 3D part and then just use the execution unit to do their math parallelly quickly. So I kept this slide just to give you an idea of what a real GPU probably looks like. Again, these are the same diagrams, right? You have boxes, you have local cache for each of these 8 execution units. And then you also have a common L2 cache, and outside you will have a main memory. Command front end is something that helps you disperse your work. So when you have so many execution units, right, you need something to organize your work. You need to spread your work as evenly as possible into your GPU. So that's where the front end comes, right? Um, Coming to the programming part of things, now that you know what a GPU looks like, you know how much parallelism we are talking about, let's get into how would that affect your work, right? So I was talking about matrix multiplications, but here let's just take a simple example of adding two vectors, right? So let's say the vector is at the scale of thousands of data points or millions of data points. So if I ask you to add those two vectors, if you write a C code for that, that will look something like this, right? There will be n data points, and all you do is take the data point I for vector A and then take for vector B and then add it to get your CI, and that's all, right? But if you think about it from a performance perspective, this is not great because in one clock, you are only doing one addition. This is assuming that one addition takes one clock, could take more also, but usually it is one clock. Now, that's not great in terms of using your memory. It's not great in terms of the time that it takes to add this whole array. So how do you parallelize your work? How do you write code that takes advantage of these multiple cores that you have here? So we write something called GPU kernels. Okay. So I think in computer architecture, there's also a term called SIMD, MIMD, uh, SISD, and all these things. So the code that you see on your left is single instruction, single data, right? So if you unroll this loop, what you're doing essentially is one addition in one instruction, right? So that's not great in terms of parallelism. That's not parallelism. Okay. So the architecture that GPUs are built out of is single instruction, multiple thread, SIMT, right? So you can notice that all you're doing is addition, right? So the instruction doesn't have to change. What you just have to change is the data point that you're operating on that addition, right? So what we write is a GPU kernel, which is a very simple piece of code. When you look at that, GPU kernel is a function written to run on a GPU, right? So the way kernels work is the kernel gets split into multiple threads, right? For example, if the size of the array was 1024, then what you could essentially do is you can write one function here, and if you set the parameters properly, it will break down your whole instruction into 1,000 threads, each of the thread doing one addition. And then in this diagram, you could essentially uh, send one addition for one core. And then as in theory, in 2 clocks, you're done with the whole addition. So if you see the performance difference, it's 1,000 clocks in this case to probably 2 or 3 clocks in this case. So that's the mindset that you have to think when you're writing code for GPUs. Now, as a AI engineer, if you guys are working on those things, LLMs, and if you're writing to train models, usually you do not interact at this level because you'll be writing in Python and then using a lot of library and then APIs, which do the hard work for you. So it tries to take whatever code you write and tries to optimize it as much as possible. But this is a performance scenario, right? You're not just trying to run your code, you're trying to run it as efficiently as possible. These huge corporations like Microsoft and OpenAI, these people spend billions of dollars to buy these GPUs, right? They want to use it as efficiently as possible. They do not want any unoptimized piece of code in your GPU. They want to save every second that they can save on the GPU runtime. So that's where you need to be in that mindset, right? In a performance mindset. So in this case, that's how you are um, saving your hardware clocks. Now, this is a simple example. You can always look into more examples, like, for example, how do you do matrix multiplication, and you can try these things on your own, right? I don't think CUDA is open source; it's NVIDIA specific, but you can always write your code in OpenCL and try to see how it works. in computer graphics lab, you will be using OpenGL, but there is also a API called OpenCL, which is Open Compute Library, that helps you write these things for GPUs. You can even run it in your laptop because you always have an integrated GPU in your laptop. So it's good to practice in that way, right? So that was a basic overview on what kernels look like. And yeah, let's take a bit more complex example, right? This is not going into the code, but how do you think from a performance perspective? Because as I showed you, the hardware will only have like thousands of cores, but it's not going to have one core for each addition in a way that I showed you in the last example. So how do you break down your work, right? Well, this is an algorithmic and problem solving perspective of how do you think, right? So one of the most famous workloads for AI is called general matrix multiplication, or GEM at short. Uh, this is basically a matrix multiplication and addition workload. So what you do is you multiply two matrices, add a third matrix, and then the result what you get is the solution, basically. Right. So we can imagine A is the first matrix, B is the second matrix, and what you're adding is matrix C, right? It's a very general workload because when you do neural networks, all you're doing is matrix multiplication and addition. So this is where it's very important to maximize performance in this scenario. And as I told you, the caches are not infinite. So you can only load select piece of data in your GPU before it gets full. And obviously you do not want to fetch everything from the main memory because the fetch will not be as fast. So I'm referring computer architecture and operating systems here again. So you would have heard about cache hit ratio, miss ratio, and you know that L1 cache is the fastest, right? I'll go back to the diagram of the hardware. If you see the yellow piece of cache, which is smaller in size, but this is the fastest, and but the size is limited here, so you need to use it uh, as carefully as possible. And whatever you cannot fit in L1, you put it in L2. And if you cannot fit it in L2, then the fetch time becomes really bad. You have to wait for a long time to get your data back to you. So you want to break down your workload in such a way that you minimize memory fetches as much as possible. You want to keep as much of it in L1 and L2, but the space is limited. So what do you keep in L1? You do not load the whole matrix because most of the times that's not even feasible. What you do is, you know that in matrices, you multiply the element in a row of the first matrix and an element in the column of the second matrix. And the common index here is k, right? So you have a of mk that will be multiplied with a of kn, right? And if you think about that, you only need to load this particular row and this particular column at a time, right? Because when you're multiplying these things, you do not need the other ones, at least for this row. This row is only concerned about this column to get this chunk of data for the green box, right? So that's how you think. Your perspective changes completely. You do not have unlimited memory to load the whole matrix. So this is how you think. You break down your workload. And now that you have this particular tile that you're processing on, you will probably fetch only these elements, the blue box and the yellow box, to calculate the green box here. And then you'll put it in a single bunch of cores. You'll probably put it in only this core so that whatever data it needs, all of it is already present in L1 and it doesn't have to miss too many times, right? So your cache hit ratio improves, your memory bandwidth improves, and in the end, you end up completing your workload a lot faster. So this is a glimpse of what we do. At least in my work, we try to see how to optimize the workload coming in as much as possible. Now, this can be done at a compiler level as well because compiler decides how to distribute the work among the GPU. You can do it in a, so I'm referring to operating systems here again. There is a way to go through your threads, right? You can do round robin, you can do oldest first, you can do stall based round robin. So if you do round robin, that's great for your, uh, getting your work done as reactively as possible, but it's not always the best because one of your threads can be stuck doing memory fetches. You do not want to wait for that to complete. So there is something called stall based round robin, where you basically give it a timer. You see if it's able to complete in a select number of clocks. If it doesn't, you switch it out. So that's about thread switching. I did not put a slide about that because I did not want to go into a lot of depth, but I'm trying to refer here as many concepts that we learned in college as possible, because when we are learning the subjects, we do not think that this is very useful, except a few. But that's a myth, right? You learn these subjects for a reason, because ultimately that helps you understand these low level concepts. If you're just a web developer, you'll probably not use a lot of it, but there are a lot of fields other than web development as well. So that's where these things become helpful. Right. Any doubts till now? I do not have a lot of slides after this.
No, Ashwin. As of now, no doubts. But guys, do you have any doubts?
No doubts.
Okay. Yeah, I guess I'll conclude the session then. I have only a slide. Uh, so yeah, us being very AI dependent these days, I know how things work, right? I'm pretty sure everyone loves to use whatever AI model that they're familiar with to get their work done. But it's not to say that it's very bad, because that's also something that we also do. I mean, as a working professional, we also use AI tools not to do our work, but to increase our productivity, right? So it's not going to always give you the most accurate answer. If you know how an AI model works, you will never trust it, because in the end, the AI model is nothing but trying to predict the next word to type. So all it's using is the prompt that you gave it, the words that it has already given out, and then based on these two things, it's trying to predict what should be the next word. It's just prediction, right? It's not going to be a perfect job because it's trying to make up words. So never trust an AI completely, but you can always use it to improve your productivity of things that you find mundane, right? But it's not going to help you learn anything. So that's where you should be careful in terms of using AI. But if used as a tool, it's it's going to help you a lot in terms of learning, right? So to conclude, without GPUs, modern AI wouldn't exist, because if you see, now I will refer a point from automata theory. You will see that problems have a category, right? You have problems which are solvable, you have problems which are uh, definitive, which means it always have an answer. And then you have NP, you have NP hard, where problems can have a solution. They do have a solution, but solving it is going to take forever because the time complexity is really bad. Now, we do not have the solutions to solve NP hard, NP complex problems. That's something that the quantum computer will probably do in the future. But what GPU has enabled is something similar to that. The problems that you would earlier think that they are very difficult to run, it will take forever, it will take weeks to run, months to run. That thing, if you're able to do it in hours and minutes, that's already a huge boost, right? You're solving things that used to take forever. Now they're taking few seconds. So that's what GPUs have enabled. So it's not like LLMs didn't exist before, or engineers couldn't have thought about these things earlier, but they didn't have the means to run these things. And with GPUs being there now and people constantly innovating, they figured out that they can use these gaming hardware to run their math models as fast as possible. So that's where thinking perspective gets you. That's the innovation that people expect. And yeah, that's the conclusion. So it's not that GPUs just sped it up, they enabled it. So before, things that were not considered possible are possible because of these things. And I'm quite lucky to be working on this product. Intel also works on a lot of things, but I luckily landed on GPUs and it's the most interesting thing. Okay, I think that's all the slides I had. If you guys had any questions, you can ask me, or if you want me to explain anything further, you can ask. It doesn't have to be just about the topics that I discussed. It could be anything that you want to ask me. Uh,
Guys, any questions? Please ask, because this is your opportunity to learn from our very own alumni. Okay,
what
so
semester
Ashwin,
are people
what's
are in here?
okay here? Mostly it is from all three semesters, the first 3 years,
Okay,
second, fourth, and sixth semester people.
I guess the first or third semester people won't be very interested about jobs yet, but if you guys have any questions there as well, I can answer if there's anything that you want to know.
Yeah, I had a question. Like, if I want to do AI acceleration, like, what skills or projects would you recommend to me to focus more on?
Uh, do you want to work on the optimization side, or is it about the models that you want to probably train or work on?
I want to work on the model and the training aspect.
So on the training aspect, there's a lot of resources already out there, right? So if you want to understand how to build models, then I would suggest exploring more on the data science perspective, because the means and hardware is already there. What you need to learn is the probably basics of AI. I think there is this one subject in seventh semester or something that, but you don't have to wait till that. You just explore uh, what are the things that is relevant to training. And I will just mention that AI is just a bunch of math. I will say it's more math than computer science. So be sure to be good in linear algebra if you want to explore on that front, because the base of linear algebra will help you go a long way in AI. And yeah, that's my basic suggestion. But there's a lot of resources out there. You can always participate in hackathons and then get more knowledge out of it.
All right, thank you.
What if we want to work on the optimization part?
There, I mean, so I personally was very interested in compilers when I was in college. So that's a great field to study further and then even work on. If you're interested in MTech or anything, that's a great field these days people are working on. I personally also worked on GPU compilers for the beginning of my job, and it was the most interesting thing. So check out LLVM. Okay, LLVM is a framework that helps you build compilers really easily. So the compilers lab that we have in college, that's good for the basics. If you understand how the phases in compiler works, semantic analysis and lexical analysis and whatever, I forgot the flow, but there are a lot of, I think there are 7 stages to a compiler. And one of the stages there is code optimization, where you learn about techniques, right? So you learn about things that speed up at a compiler level your code. For example, there is loop unrolling, and uh, there is like data replacement at there is branch prediction. So these are the concepts which help on compiler optimization. That's one thing that I will suggest looking into, and that's a great project if you guys are looking for ideas for your college projects. LLVM is a great tool that helps you build compilers much easily than you think. So
Okay.
check that out on optimization perspective. And I mean, I think as a computer science student, you won't go further than that, but you can always look into how assembly works as well. But I think that's too scary for most people to get into. You can always so these C compilers that you have, right? You can always look into flags that you get to run these C compilers, where you can stop the compiler at a particular stage. You can stop it before the object is generated. You can stop it before the assembly code is generated, and look into the phases and see how it works. All of these compilers are open source. I think GCC is open source, so you can find out more resources on how these things works and try to write your own compiler. These days, people are even writing their own languages and writing a simple compiler to compile their own language to uh, an object. So yeah.
Okay. Thank you.
And Ashwin, what were some good projects that helped you into getting into Intel as an intern?
Okay. So Intel internship was okay. So at that time, actually, I was preparing for my gate also. So the core subject knowledge really helped me in the interview. But to land the interview in the first place, I think the project that they were interested in was something that I did in the microcontrollers. Do we have a lab for microcontrollers? I think we did. And there was the software that we used, right? Kyle, UVision or something, where I think we write code in assembly. So what I did was I wrote a small piece of code in assembly, and that was basically simulating a automata. So we have state machines, right? I think if you're in sixth semester, you might know what a state machine is, but basically these are these Mealy and Moore machines, right? So I just wrote a simple Mealy machine in paper, which probably predicts something like if a number is odd or even. Very simple thing. But writing a code in assembly for that is not easy, because you have to initialize your registers, you have to do everything manually, and it was difficult. But that's something that they were impressed. So that's the point, right? It's not like you have to build the most complex project. You don't have to build like the best website to uh, impress someone, but it's the idea that you think like, why would someone want to write anything in assembly? But that was unique enough for them to select the resume to look further. And I think one more, I think I was doing a research internship at that time also related to compilers, so that also helped. And of course, I had other projects also. Well, I had put these college projects that we were told to do, this database projects, and then website also was there, but that was not the highlight of the interview. Basically, that was mostly, so if people have seen the project elsewhere, they won't be very interested in that. So the idea of trying to do something unique always helps.
Okay, thank you, Ashwin.
Sure. Anything else?
Guys, any questions? Please ask. Okay, seeing none, I think that's it. Okay, okay, fine then. Yeah, Ashwin, anything that you would want to say for us, like for the college people, anything from that we're lacking currently, like the skill gap between the industry and the college level?
No, I'll say the opposite actually. I feel um, so. This we think about skill gaps when we think about the usual jobs that we get, right? Which I don't blame because that's the majority of jobs that are there in the market. But it's all something to do with web development, or is it Java or Go, that these things are popular these days. And I don't blame, because that's the thing that's there. And even to prepare for that, you have subjects like web development and all that. Data structures are always important for your interviews. So you cannot neglect that. I'm not telling that. But what I'm trying to tell is, when you want to, so these subjects in computer science are there for a reason. Right? At least in my batch, people did not used to like computer architecture. They thought that's, why do we have it there? It's very difficult and not easy to understand. But I made a career out of it, right? So it's always there for a reason. That's the core computer science that you have. What you're doing, software development is not always equivalent to computer science. So always focus on those subjects, because they will always help you, whether you do a MTech or not. That doesn't matter. But there's a lot of research opportunity in computer science still. And as you see, there are a lot of jobs which focus on your basics as well. You have companies like Zscaler and I think Oracle and all these things, who are really focused and concerned about performance. They'll ask you to write code in C still, and I don't think that's a skill that most people are focusing on these days. So, what my point is, uh, find your interest, and you can always make a career out of it. There's a lot of things that might be interesting to you, but you might think there's no job there, so I won't focus on that. That's not true. So, yeah, um, the college subjects are good actually. I did not realize that when I was in college, but they're actually useful. And even recently, when we in office, we guys were talking, when I told, and most of the people in my adjacent team are electronics engineers because they work on the hardware. So I had told them that we had a subject called computer graphics, where we had all these lab sessions and all. We wrote code in OpenGL, and they were really impressed that these things exist in computer science syllabus. That we do all that, because those people who work on 3D units in GPUs, they do not have the exposure of writing code in OpenGL, but we did. So the the curriculum is good. It gives you a full perspective for a reason. Um, and of course, wherever you're interested in to pursue in your career, you can always focus more on that subject and learn more. That's always there. But yeah, those are my final thoughts.
Thank you. So,
Thanks for
guys,
inviting.
anybody else? Any questions? Okay, good. So, thank you so much, Ashwin. That was a very insightful session. We really learned a lot, especially the part where you're trying to put such a complex information to us at a college level perspective. That is what made us really understand this session, despite it being very complex. Thank you so much for that. And also, thank you for taking this session, coming back to the community and having a session with us. Thank you so much for that as well.
Thanks for inviting.
All right. That's it for the session, guys. I think we can wind up right now. Cool. Thank you, everybody, for attending. Thanks for the speaker. Thank you for everyone. Thank you, guys.